Today we are going to discuss the questions on chemical equilibrium. So here the first question is that the concentration of a pure solid or liquid phase is not included in the equilibrium constant expression, and the reasons are given. If you consider any equilibrium which is containing either a pure solid or liquid, for example I am considering the dissociation of the calcium carbonate at high temperatures. Here when we write the equilibrium constant in terms of the partial pressure, we include only the partial pressure of the CO2, ignoring the vapor pressure due to the CaO and CaCO3 for the reason that the active mass replicates the concentration of partial pressure in a given reaction of a pure solid or pure liquid is conventionally being taken as 1. Hence, we will not be including that in the net equilibrium equation. So, the correct answer for this given question is option A. In the second question, we have an equilibrium system where the substance AB in its solid phase is disintegrating or dissociating to give you the substances or the elements A and B. Now the question is, when I double the quantity of AB, what would happen to the equilibrium mixture? So when we write the equilibrium constant, the concerned equilibrium constant for the given reaction, you will see that we do not include the AB in the net equation as it is a pure solid, hence its active mass is again being taken as 1. So therefore, by the addition of or removal of pure solid or liquid has no impact on the given equilibrium. Therefore, option D is the correct answer for the given question. So, you are given an equilibrium reaction in a gas phase. Here L moles of C and M moles of D has reacted. Then you have been asked to get the relationship between Kp and Kc. Now when I am writing the Kp for this expression, partial pressure of product rise to the power their stoichiometric coefficient divided by partial pressure of the reactant rise to the power their stoichiometric coefficient. Now when I am replacing the partial pressure with the number of moles from the ideal gas expression, where we all know that PV is equal to nRT or P is equal to N by V into RT. Hence, I am going to replace this pressure with a concentration term. So, when I am replacing, I am going to get concentration of C power L into RT whole power L, D power M into RT whole power M divided by concentration of A power X into RT whole power X and concentration of B power Y into RT whole power Y, that is into RT whole power L plus M minus X plus Y. So therefore, when I write Kp, you know that this stands for Kc into RT whole power L plus M minus of X plus Y, that is nothing but the delta N. So you can see here clearly, this indicate that delta N is the moles of gaseous products minus moles of gaseous reactant. Hence option C is the correct answer for the given question. We are given a reversible reaction with the rate constant for the forward and backward reaction to be 2.4 into 10 to the power minus 4 and 8.15 into 10 to the power minus 5 respectively. Hence, you have been asked to find the equilibrium constant for the given reaction. Now, if I take a particular reaction which lies at equilibrium and it is a gas phase reaction. Now, when I write the rate of forward reaction and if I assume that the forward rate constant as Kf, you know that rate of forward as per the rate law is A power A into B power B, and that of rate of backward reaction is K of backward, because I will assume that the backward reaction has rate constant Kb into concentration of C power C into D power D. So at the equilibrium, as we all know that rate of forward reaction equal to rate of backward reaction, hence Kf into A power A B power B is equal to Kb into C power C into D power D. or Kf upon Kb, which is nothing but the equilibrium constant K is equal to this, which we are aware of. So therefore equilibrium constant is nothing but the ratio of the forward and backward rate constant which you are given in the question, which are 2.38 into 10 to the power minus 4 upon 8.15 into 10 to the power minus 5, turning out to be, upon simplification, 2.92. So the answer for this question is 2.92, that is option B. For an equilibrium reaction, which of the following statements is not true? See, my dear students, here the options given are: if the reaction coefficient of the reaction is greater than that of equilibrium constant, then reaction is moving in the backward. If the reaction coefficient is lesser than K, the reaction moves in the forward. If the reaction coefficient of the reaction is equal to K, then the reaction is at equilibrium. Then there is no correlation between the reaction coefficient and K equilibrium. So you can see here that when I take a particular reaction, say the gas phase reaction, when I want to assess whether this reaction has reached the equilibrium or not, I'll be finding out the value of Q, which is nothing but the ratio of the product concentration upon ratio of the reactant concentration raised to the power their stoichiometric coefficient. Now when I substitute all the values which are provided to me, I am going to map it with the equilibrium constant which is being mentioned to me, because when you have started the reaction, when it is started, you know that slowly the reaction coefficient increases because there is increase in the concentration of products. It increases, reaches the maximum point and then stay at the equilibrium, that means remaining to be constant. So you say that when Q value is less than K, the reaction is still moving in the forward direction, whereas if it has equated, that means we say that we have reached the equilibrium. When this value crosses the equilibrium constant, we say that the reaction is moving in the backward direction. So these three cases we will use to determine the direction of the given reaction. So accordingly, now what I mean to say, that you will be calculating the K value from the delta G naught values which are provided as per this expression, and this is how you find out K and this is how you find out Q. Now by mapping these two, you say that the reaction can go either in the forward or backward direction depending upon the magnitude of these two, right? So it is wrong to say that there is no correlation. Absolutely there is correlation between these two. So therefore the incorrect statement for this question is option D. Now we have an equilibrium reaction, the gas phase, which is endothermic in nature, and it is asked to determine what happens if there is increase in the temperature to the equilibrium constant. So you have been given equilibrium case where we all know that the relationship between the equilibrium constant and temperature is being taken as log K2 by K1 is equal to delta H upon 2.303 R into 1 by T1 minus 1 by T2. So here this ratio, that means whether equilibrium constant increases or decreases with temperature depend upon the sign of this value. Now when I write this expression, we will be writing it as log K2 by K1 is equal to delta H upon 2.303 R into T2 minus T1 divided by T1 into T2. So here if temperature is increased, you know that T2 minus T1 is greater than 0. I mean to say this value is positive. Now it is given that this is anyways positive because the reaction is quoted as an endothermic one. So when these two are positive, the product of these two values is going to be another positive value. So therefore finally you say that is achievable only if K2 value is greater than that of K1. That means the equilibrium constant at temperature T2 at higher temperature, when it is greater than that of lower temperature, this thing is possible. So therefore we can say that for endothermic reaction, the equilibrium constant increases with increase of temperature, whereas for exothermic reaction it decreases with temperature. So option A is the correct answer for the given question, where for this endothermic reaction the K increases with increase of temperature. Now you are given an equilibrium reaction, that is 2 moles of NO2 is reacting with half mole of O2 to give you N2O5, another gas. So it's a gas phase reaction. Now, if the equilibrium constant for this is Kp, you have been asked to find the equilibrium constant for some other reaction. Now, what we are going to do is we are going to revert this. So, when you write Kp for this equilibrium, you are going to get partial pressure of N2O5 upon partial pressure of NO2 whole square into partial pressure of O2 whole power 1 by 2, right? That is partial pressure of product upon reactant. Now, what I am going to do is I am going to revert, because you see in the given question which is asked to find the equilibrium constant for the reaction, 2 mole of N2O5 is in equilibrium with 4 mole of NO2 and O2. We have to get the N2O5 on the reactant side. So, when I do that, the equilibrium constant Kp dash will become exactly the reciprocal of the previous one, or the inverse of the previous one. You can see here the numerator is going to become the denominator, because when I write Kp, it is going to be partial pressure of NO2 square into partial pressure of O2 whole power 1 by 2 divided by partial pressure of N2O5, which is nothing but the inverse of this. So, now we have been asked to find the equilibrium constant for another equation with 2 moles of N2O5 is being involved. And when I write the equilibrium constant Kp double dash, I am going to get partial pressure of NO2 whole power 4 into partial pressure of O2 upon partial pressure of N2O5, which is achievable by squaring the Kp dash value. So, is equal to 1 by Kp square, right? So, therefore, the equilibrium constant for the ultimate reaction or the final reaction which is asked is option C, that is 1 upon Kp whole square. So, predict which of the following facts for the equilibrium reaction 2 mole of NH3 dissociating into N2 and H2 holds good. So, you see here the question is related to this Kp, since it is the dissociation reaction, it is an endothermic one. So, endothermic, when you write the equilibrium constant as this, you know that the Kp and Kc are affected by only temperature but not by other factors. And since this is being an endothermic reaction, I can say this Kp increases with increase of temperature but not pressure or volume, because pressure or volume is going to affect the direction of the equilibrium but not the equilibrium constant. Whereas Kx, that is the equilibrium constant expressed in terms of the mole fraction, will be affected by the total pressure. Hence, the correct answer for this question is option B, where Kp is unaffected by the influence of the pressure or volume on the equilibrium. The oxidation of SO2 by O2 to SO3 is an exothermic reaction. The yield of SO3 will be maximum if the conditions are given to you in the problem. So, when I am oxidizing the SO2 gas using O2 gas to give you SO3 gas, one can see here that this is an association reaction and exothermic reaction. So, therefore, the question is to increase the yield of SO3, that means the product content is increased by shifting this equilibrium in the forward direction, which is achievable by increase of you can see here that when I increase pressure, the volume is decreased. I am going to say the total pressure which I am increasing on the entire equilibrium mixture. Hence, the volume of the gaseous mixture is decreased. When the volume of the gaseous mixture is decreased, the equilibrium shift to the lower mole side, that is nothing but forward direction. So, I can increase the yield of SO3 by increasing of pressure, and this is an exothermic reaction, right. So, the exothermic reaction are driven in forward direction by decreasing the temperature, whereas endothermic reactions are shifted in the forward direction by increase of temperature. Hence, the correct answer for this question is option B. By decrease of temperature, we can achieve more yield of SO3. We have a reaction where NO is dissociating into N2 and O2, which is an exothermic reaction. Then it is asked that which of the following does not hold good for the given equilibrium. So here you can see that delta N for this equilibrium is 0, that is 1 plus 1 minus 2 moles of gaseous products minus moles of gaseous reactants, so which is equal to 0. Then in that case we all know that there is no effect of pressure or volume on the equilibrium nor the addition of catalyst. The only one thing that would influence this equilibrium, because it is given that this reaction is an exothermic reaction, so high yield of this reaction are achieved by the decrease of the temperature. So temperature, when it is decreased, the equilibrium is going to move in the forward direction. So dissociation of NO is favored more at low temperature is the correct answer, and option C is the wrong statement, hence the correct answer for the given question. When NaNO3 solid is heated in a closed vessel, oxygen is liberated along with NaNO2. At equilibrium, the specific conditions are described here. So when you have got the solid NaNO3, sodium nitrate is heated in a closed vessel so that oxygen doesn't escape and equilibrium is established. So now the question is, what happens when you want to increase the what you call the product content in this reaction? So here you can see that it's a dissociation reaction, hence it can be presumed that it is an endothermic reaction. So therefore increase of the amount of product is achieved by shifting this equilibrium in the forward direction, and it is achieved at high temperature because it is an endothermic reaction. So therefore endothermic reactions, as we know, that are favored at higher temperatures. So therefore this reaction is favorable at high temperature. And the another option looking at, now you can see that there are moles of the gaseous products than that of the reactant, because you can see the other components are pure solid. So delta N is positive, that is greater than 0. Now when I am suppose is increasing the pressure, now when I increase the pressure, the volume is decreased and the equilibrium shifts to lower gas mole side. So which side the moles are low as far as gases are concerned? The products. You can see there is half mole of gaseous product is there. The product, sorry, the reactants are going to be formed more by shifting this equilibrium in the backward direction when the what you call pressure is increased. So therefore increasing the pressure favors the reverse reaction is the correct option for the given question, that is option T. Now we have a gas phase reaction where ethene is hydrogenated to ethane, which is an exothermic reaction carried out in a vessel. Then the equilibrium concentration of C2H4 can be decreased by. So you want to decrease the concentration of C2H4, that means you want to shift the equilibrium in the forward direction. So you see all the conditions that are suitable to shift this equilibrium in the forward direction. Why we are saying forward direction? Because forward direction only will decrease the content of C2H4 in the equilibrium vessel. So here the forward reaction can be achieved for exothermic reaction by lowering of temperature. Now when I lower the temperature, it's going to take place. So here in option A we have increasing the temperature. Increasing the temperature will shift the equilibrium in the backward and amount of C2H4 will increase. Now option B, when I am increasing the pressure, you know that volume is decreased, so equilibrium will shift to that lower gas mole side. So lower gas mole side, that means forward, because you can see that the moles of gaseous products are 1, the moles of gaseous reactants are 2. Hence option B seems to be the correct one. Now when I am removing some H2, that means when I am removing the reactant, the equilibrium will shift in the backward direction, which we don't want. We want this equilibrium to move in the forward direction. Then as far as option D is concerned, when you are adding some ethane, again addition of product shift the equilibrium in the backward, which we don't want. So therefore the correct answer for the given question is option B. We have the equilibrium reaction PCl5 dissociating to give you PCl3 and Cl2. The forward reaction at constant temperature is favored by. So you can see here that this is the dissociation of the PCl5. Now you want to what you call the increase. You want to increase the forward reaction content at a constant temperature. You don't want to change the temperature here. You want to move this equilibrium in the forward direction. So which is achieved by option 1. This is a dissociation reaction, but we cannot change the temperature here as this reaction has to be carried out at constant temperature. It is given in the question that this reaction is done at constant temperature. Now if I would like to achieve more of PCl3 and Cl2, what I will do is I will decrease the pressure. When I have decreased the pressure, the volume is automatically increased. Then the equilibrium shifts to more gas mole side, that is nothing but the products, because you can see there are more product moles than that of reactant. There are 1 mole of reactant and 2 mole of product. So therefore more forward can be shifted, or the amount of PCl3 and Cl2 can be improved by what you call decreasing the pressure. Now when I am adding, I mean to say when I am writing the equilibrium concerned constant, the partial pressure of PCl3 into partial pressure of Cl2 upon partial pressure of PCl5. Now I am going to replace this partial pressure with nRT by V from the ideal gas expression, where I will write this as number of moles of PCl3 into number of moles of Cl2 upon number of moles of PCl5 at equilibrium into RT by V whole power delta N. Now I am rewriting it in terms of the pressure, because we know for the equilibrium mixture, we are going to replace this RT by V with P by sum of N. Here sigma N is nothing but the number of moles of all at equilibrium, all the active components at equilibrium. So now when I have added the inert gas, you can see, my dear student, that delta N for this equilibrium is a positive value. Now when I am adding the inert gas to this equilibrium mixture, the value of sigma N would increase and delta N is positive. When this value is increased, obviously the whole value gets decreased. I mean to say, when this is changed, it will become Q. The Q has decreased because the denominator has increased by the addition of the inert gas. Just there is increase in the number of moles. It is not going to impact the equilibrium because it is inert. It is not going to react with anything. So what I mean to say, that Q is going to be less than K. That means the equilibrium is going to shift in the forward direction if the reaction is done at constant pressure. Whereas if it is done at constant volume, there won't be any effect on the equilibrium. At constant volume, the pressure can be adjusted accordingly so that the sigma N dash is nullified. So the correct answer for this question should be that if I want to increase the content of PCl3 and Cl2, there should be decrease in pressure. Option A is the increase in pressure. By introducing chlorine gas at constant volume, the equilibrium will shift in the backward, which we don't want. Then we have decreasing the volume of the container is again going to shift the equilibrium in the backward, lower mole side. Then option C, by introducing an inert gas at constant pressure, will be the right answer, because when I am increasing this value, Q is less than K and the equilibrium will shift in the forward direction. So therefore option C is the correct answer, where you have there is introduction of the inert gas at constant pressure. We have the equilibrium mixture, N2 and H2 are combined to give you NH3 gas. Now the question is, when some inert gas at constant pressure is added to the system, we have to predict the direction of the reaction. As I just told you, Kp is number of moles of product upon the stoichiometric coefficient upon the number of moles of reactant raised to the power the stoichiometric coefficient into P upon sigma n will become sigma n dash after the addition of this thing and delta n. You can see here delta n is equal to 2 minus of 1 plus 3, which is equal to minus 2, that is less than 0. That means your equation is going to become sigma n dash upon P whole square, because the delta n value is negative. Now what happened here? We have added the inert gas, hence this value has increased. When this value has increased, you can see that Q will become greater than K. That means the equilibrium shifts in the backward direction as the pressure is kept constant. So therefore, when the equilibrium shifts in the backward direction, there is consumption of NH3 but not the production. So therefore, less of NH3 produced is the correct option, that is option B is the correct option for the given question.